So let's talk about some of the vector operations we can perform. We'll start with multiplication. Now, vector multiplication is actually multiplication of a vector by a scalar. And that's because we can't multiply one vector by another vector. That operation isn't defined. There are other operations similar, such as dot product and cross product. But when it comes to multiplication, we can only scale a vector by a scalar value. Now here's how it's done. Let's say we have a vector v1 with components 1, 2. So v1's x component is 1 and its y component is 2. Let's say we would like the opposite vector. In other words, the same magnitude, but the vector is pointing in the opposite direction. Well, we know that all we have to do is flip the sign of the x and the y components. This is actually multiplying the vector v1 by the scalar -1. Here's how it's done. We know that v1 is the vector 1, 2. And we know that we can multiply a vector by a scalar. Well, to multiply v1 by -1, that gives us -v1. All we have to do is take the scalar, -1, and multiply the x and y components each by -1. -1 times 1 is -1, and -1 times 2 is -2. So -v1 is simply -1 times x and -1 times y, which gives us -v1, the vector in the exact opposite direction of v1 with the same magnitude. Now let's talk about scaling by something other than -1. We've already seen that example. Well, if we take v1 and we multiply it by the scalar 2, we're going to multiply the x and y components each by 2 respectively. So 2 times v1 is going to be 2 times the vector 1, 2. And all we do is multiply x by 2. So 1 times 2 is 2. And we multiply y by 2. So 2 times 2 is 4. So 2 times v1 gives us this vector, 2, 4. And this is the vector in the same direction as v1, but its magnitude is scaled by 2, so it's exactly twice as long. So vectors have this handy quality that we can scale them by a scalar, and their magnitude is scaled by that scalar. So that's vector multiplication. It's quite simple. Let's talk about addition and subtraction. Now, say I have a vector v1 with components 1, 2, and I have a second vector, v2, with components 3, 2. I want to add these two vectors together. Now this is a well-defined operation. Vector addition is something we can do. v1 plus v2 is the sum of v1 and v2. All we have to do is take their components and add them together. v1's x component is 1, and we can add v2's x component, which is 3. For the y, we do the same thing. v1's y component is 2, and v2's y component is 2. Simplifying this down, 1 plus 3 is 4, and 2 plus 2 is 4. So v1 plus v2 is the vector 4, 4. We call this component-wise addition because we're taking the x components and adding them together, and we're taking the y components and adding those together. And we use the same process for a three-dimensional vector as well. If these vectors had z components, we would simply add the z components together to add the two vectors. Now let's talk about the geometrical significance of this. If we add two vectors together, we have an interesting geometrical situation. Let's say I've added my vectors v1 and v2. Well, if I place the vectors like this, such that v2 has its tail at the head of v1, then the result of this vector addition is the vector starting at v1's tail and ending at v2's head. This makes sense if we take a look at the components of each vector. v1 has components 1 for the x and 2 for the y. And v2 has the components 3 for the x and 2 for the y. And we know that to add these two vectors together, we perform component-wise addition. We add their x's together and we add their y's together. v1's x is 1 and v2's x is 3, and we know that the result, v1 plus v2, has an x component of the sum of these two, which is 4. And v1's y component is 2, and v2's y component is 2, and we know that the sum of these two is 4. Now let's take a look at what the vector looks like when we draw it. v1 plus v2 is 4, 4. If we place its tail at the tail of v1 and its head at the tail of v2, we get this vector. This vector has an x component of 4 and a y component of 4. Now, we can use this geometrical significance to our advantage in game development, and we're going to do that very soon. In general, any vector v1, when added to vector v2, if we place v2 such that its tail is at the head of v1, then the resultant vector, v1 plus v2, is the vector from the tail of v1 to the head of v2. Now, what if we want to subtract? Well, subtraction is really just an addition problem. If we want to subtract v2 from v1, in other words, what's the result of v1 minus v2? Well, all we have to do is draw v1 and add negative v2. We know that v2 is the vector 3, 2. What is negative v2? Well, all we have to do is simply multiply x and y for v2 by negative 1. So v1 is the vector 1, 2, and negative v2 is the vector negative 3, negative 2. So it's this vector. This is negative v2. So v1 minus v2 is v1 plus negative v2. v1's x is 1, v2's x is 3, and negative v2's x is negative 3. v1's y is 2, and v2's y is 2, and negative v2's y is negative 2. And this simplifies down to 1 minus 3, which is negative 2, and 2 minus 2, which is 0. Now, we have v1 and negative v2, and we just added them together. That gives us this vector. If we draw it such that its tail is at the tail of v1 and its head is at the head of negative v2, we get this vector. Well, this is the vector negative 2, 0. To get from its tail to its head, we have to go negative 2 in the x and 0 in the y. So subtracting one vector from another is really an addition problem if we add the negative vector. This geometrical significance is going to come in handy all throughout your career as a game developer, and we're going to see how to apply this in the engine. We'll see you soon.